Hey, thanks so much, Azam, for those announcements. And before we get started with today's session, I should introduce myself. I'm Hantsche. I'm one of the directors at Ore Deposits Hub, and this is our season finale. This will be our last talk for 2021. And I just wanted to sort of do a quick summary of what we've been able to accomplish this year with the Ore Deposits Hub community. And it's been a great year. We've been in a global pandemic for nearly 2 years at this point, and ODH came about right at the beginning. So we've had basically 2 full years of ore deposit seminars, community events, and YouTube videos now for the better part of 2 years. And we're excited for some of the changes that we were able to implement in 2021, such as these continuing the bi-weekly meetings. We actually worked with our sponsors, the SGA and SEG, to bring you a community networking event in May, where we had young professionals meet up with industry geologists in a free networking event targeted towards students coming out of the university system. In October, we were able to organize a joint collaboration with the Irish Association of Economic Geologists, and instead of a weekly seminar, we were able to host a 2-day conference with that organization that turned out really well. We had a lot of great talks and fun on those days. We had presence at the SEG 100, which was a virtual hybrid meeting, but we had a virtual booth for ODH, thanks to our sponsors there. And we will continue working in 2022 with our sponsors and hopefully with new support from some industry collaborators to keep bringing you fun, engaging, and educational news, science, research on ore deposits as we move forward. So we're looking forward to the next year. But most importantly, 2020, 2021, none of this would have happened without support from our community. The willingness of our speakers to share their research, their knowledge of earth science and ore systems, and then you all for tuning in, following our social media accounts, watching and participating in the discussion, which is the #1 thing that makes ODH talks better than a lot of the other online conferences, which can get old and repetitive. So we'd like to say thank you. This is a big end of year thank you. Happy holidays. And we will look forward to this season finale. And I look forward to seeing all of you again in 2022. Thanks. Michael?
Hello, everybody, and welcome to the final talk of Ore Deposits Hub. I have the pleasure of introducing today's speaker. So Cyril Chelle-Michou is associate professor at ETH Zurich. His research concerns mineral resources and is very cross-disciplinary. He uses methods and techniques and concepts from economic geology, geochronology, geochemistry, and numerical modeling to gain insights on processes controlling the size of ore deposits, the endowment of mineral belts, the flux of hydrothermal fluids in dynamically evolving systems. These develop new techniques for exploration and targeting, and also develop high precision geochronological techniques. Also, we are happy and privileged to be joined by Jeffrey Hedenquist, who's adjunct professor at the University of Ottawa, who has a great deal of expertise in these issues. And so we'll be following the talk of Cyril and act as an informal panelist for this talk. So thank you all, and Cyril, over to you.
Thank you very much, Michael. Thank you very much to all of you for joining today, tonight, this morning, whatever. And especially, again, I would like to extend my thanks to all the teams of Ore Deposits Hub who have been doing over the past 2 years an amazing job, or maybe 1 year and a half. It's really great to be able to keep connecting despite not being able to meet each other in person at conference. So thanks a lot for all your work in this, with Ore Deposits Hub. So today I will be talking about what makes the difference between large and supergiant porphyry copper systems. And actually my true title is what probably makes the difference between these two types of porphyry systems. I just thought I would remove probably from the official talk, otherwise no one would really dare joining today. So actually it's very much work in progress and more of hypotheses that are being tested. But that sounds to me like reasonable hypothesis based on basic physics and chemistry, at least. Okay, so maybe a very short recap on porphyry copper deposits. I guess if you want more deeper insight into how these deposits formed, there are many super interesting talks available on the YouTube channel of Ore Deposits Hub. But in 1 minute, what is important is that you have in magmatic arcs usually metal and saline S-bearing magmatic fluids that get outgassed from a cooling pluton, and somehow these gases are channeled toward an apical part of this system, where they cool, interact with the surrounding rocks, and precipitate metals. This is associated with very intense hydrothermal alteration, like you can see in this picture, veining. And this is how we define essentially an ore deposit, porphyry copper deposits. It is almost always, as far as I know, associated with precursor magmatism that precede the formation of the porphyry deposits by 1 million years, maybe up to 5 to 10 million years. And I say this right now because I think this is actually an important part of the system. We tend to focus a lot on studying the deposit itself, but what I think is important, I will insist a lot in this talk, is to study the context of the deposit and to study the precursor magmatic history in almost the same details as the porphyry copper deposit itself. Another part of the system that we actually never see and that we suspect more than anything, based on the work of petrologists, is this part in the deep crust below maybe 20-25 kilometers depth, where the magma coming from the mantle stall evolve, differentiate, and maybe mixes with partial melt from the crust. This is essentially the magma brewery in the lower crust that prepares the magma to be transferred to the upper crust. And this is where, as many of you know, the high strontium over yttrium signature that characterized the magmas associated with porphyry copper deposit is developed in the deep crust. Okay. With this in mind, let's come straight to the question that occupies my day, is what controls the size of the deposit? Here is a log diagram resulting from a compilation of the USGS more than 10 years ago already, 20 years ago, no, 10, more than 10 years ago already, showing that porphyry copper deposits of the world range over 5 orders of magnitude in copper endowment. And in order to visualize this, I've just shown here 3 deposits, all at the same scale, showing here the Chuquicamata district, Bajo de la Lumbrera, and a very small deposit in Bulgaria, Saracen, that probably would not be mined today anymore. All of them are across very different sizes, yet the geological processes that we would put forward to explain their genesis are remarkably similar, actually. And if you take a sample from Chuquicamata, another one from Bajo de la Lumbrera, and a sample from Saracen, you don't put any numbers of them, you mix them all together, probably very few people, or almost no one, would be able to tell which one is from where, because they would be very similar. And so it seems to me that there is a fundamental thing we don't really understand about these deposits. We understand how they form. We understand the chemical processes leading to the precipitation of these deposits. There are plenty of things that many researchers have investigated, but we don't really understand what makes the difference between a super large system like Chuquicamata and a very small system like Saracen, for example. And this is the question I would like to address. Of course, I'm not the first one to address this question. Maybe here, the titles of what I would deem to be the most focused paper on this topic. The first one, maybe by Alan Clark in the 90s, where he compared the characteristics of few porphyry copper systems in the world, and essentially could not really observe any systematics in between the smaller example of this clan and the bigger one. Jeremy Richards a few years ago revisited this topic, and essentially in this paper there is a very nice table comparing the characteristics of small, or let's say large, porphyry copper deposits and supergiant ones. And there is nothing that really stands out, which led Jeremy to suggest that these supergiant deposits are formed by the optimal alignments of a combination of commonplace geological processes. And I would tend to agree with this conclusion, but I would also like that we're able to predict as much as we can these geological processes and and quantify how they contribute to the formation of supergiant deposits. Because from an exploration point of view, well, let's imagine we start exploration either by drilling something below cover, because we have some indications that there could be something at depth, or we find a small outcrop somewhere on surface. Usually when we start, we have no idea whether we are dealing with just a small occurrence, maybe with almost no copper in it, or if we are already dealing with a supergiant discovery. Even if we have a very beautiful samples like the one in this picture, we have no idea actually how big is this new deposit. And of course, since we aim today to discover giant deposits below cover, it would be super advantageous if we could have at least some clues already, or some tools to help predicting the probable size of the deposit as early as possible, actually. And as early as possible, because these discoveries are associated with increasing economic risk and environmental impacts, especially as the ore bodies are becoming deeper and deeper. I mean, especially the new discoveries. And this is why I think we would need, ideally, to find a way to estimate the size of the deposits as early as possible in the exploration process. Of course, there are already some tools available, but I think we could develop new tools that would help in this direction, that would go in this direction at least. Okay, so let's start with chemistry. So one way to put more copper in the system is to have a magma that is richer in sulfur and copper. As I mentioned, the magmas that makes it to the upper crust is largely brewed and prepared in the lower crust. Okay, and because in the upper crust, thermally, you cannot really significantly differentiate the magma. It's incredibly difficult to do that. It's much more efficient in the lower crust. Yet in the lower crust, something that cannot be avoided is to have magmatic sulfides. And this magmatic sulfide actually puts strong constraints on the availability of sulfur and copper in the magma, because they crystallize in the lower crust, and they scavenge some of this sulfur and copper that would have been nice to form porphyry copper deposits. Here is a diagram showing the silica concentration versus the copper content or the sulfides, the sulfur concentration at sulfide saturation for experimentally determined liquid line of descent. Okay, so these are experiments who have determined the compositions of magma in the lower crust for example, for the orange one, starting with this composition and running fractional crystallization experiments or equilibrium crystallization experiments down to a more evolved composition. And here, in between 60 and 78% silica, this would be more or less the region in which we would have magmas corresponding to arc, dacite, or andesite, corresponding to the typical composition of magmas associated with porphyry copper deposit. And you see that by the time you reach this kind of composition, the sulfur concentration is only on the order of few hundreds of ppm, and the copper concentration is only on the order of few tens of ppm. So something quite low, and especially much lower than the arc basalt you started with. And in the background, there is a compilation of melt inclusion from all over the world, from arc lavas, highlighting that indeed the melt inclusion that are measured worldwide follow this pattern. So it seems from this perspective very hard to have copper and sulfur-rich magmas of the right composition, andesite to dacite, that makes it to the upper crust to form porphyry copper deposits. So let's just start with what we have. So a magma that contains few hundreds of ppm of sulfur and a magma that contains few tens of ppm of copper. Now we can look at the ore-forming fluid now in the upper crust. And this has been studied very intensely also by Andrea Sodeta, who highlighted in, for example, this seminal publication 2 years ago, almost 3 years ago, where he compared the composition of hydrothermal fluids in a barren system, but also in mineralized system, and essentially highlighted that there are very minor differences, if not almost no differences. And if we run numerical models of magma degassing using experimental constraints for partition coefficients, etc., actually we also reproduce these values that are measured. For example, this is a model that I run starting at water saturated condition at around a bit more than 900 degrees in the upper crust. If you just follow the oxidized pattern, the full line, you see that as you degas, the fluid has something like a bit less than 2% of sulfur in it. The copper content in blue here is on the order of few hundreds of ppm in the fluid. And both of these values actually match very well with the values that are measured in intermediate density fluid inclusions in mineralized and barren systems. And of course, you can also play with some parameters, for example, the salinity of the fluid, which you can control with the initial chlorine concentration in the magma. And of course, it increases a little bit the copper content of your fluid, but not dramatically either. So it seems that both empirical observations and modeling based on experimental determined partition coefficients suggest that no sulfur, chlorine, or copper enrichment is required. And this is not what is observed. This is not what is predicted. Of course, it is helpful. I don't deny it, but it's probably not what makes the difference between a large and a supergiant deposit. Maybe it makes the difference between a supergiant and a slightly less supergiant deposit, but that's it. And then let's come back to this compilation of the USGS of the size of porphyry copper deposits. In this compilation, they not only compile the size, but they also compile the ore grade and the ore tonnage. And this diagram actually tells much more than what it seems. If you just look at these two plots here, so one is the comparison of the copper tonnage versus the copper grade, and the other one, the copper tonnage versus the ore tonnage. And you see here that there is almost no correlation between the two. So this, together also with the other evidence I discussed before, strongly suggests that the metal concentration in the magma and in the hydrothermal fluid or the precipitation efficiency are not the important one, are not the main one that controls the size of porphyry systems. it cannot be from this data. Of course, again, it is helpful. Maybe it will make the difference between a deposit here and the deposit here, which is still significant, but it is not the main one that makes the difference between a large and a supergiant deposit. However, you see an excellent correlation between the copper tonnage and the ore grade. So this strongly suggests that the volume of the effective hydrothermal fluid that passes through the system is the primary controlling factor. And so now we can ask the question, what controls the volume of this effective hydrothermal fluid? And I think we need to move away from chemistry to understand this physical quantity that is volume, and to investigate the magmatic system at depth. Because first of all, a large volume of fluid requires a large volume of magma, because you can only put so many amount of fluid in a magma, which usually we assume or we measure to be on the order of 4 to maybe 6 weight % of water, maybe more in a few cases. So you need large volume of magma transferred to the upper crust in order to have a large volume of fluid. Something that is very important also is to avoid or at least minimize catastrophic volcanic eruptions that would vent all of the ore ingredients to the atmosphere. That's quite important, of course. And the final thing you need to do to have an effective hydrothermal fluid is to focus this hydrothermal fluid toward a very narrow apical part of the magmatic system. And so let's go through these three, what I think are the main parameters that determines the physical fertility of porphyry copper systems. So first, something that is required is to brew the magma in the lower crust. And of course, if you want to transfer a big volume of magma to the lower crust, to the upper crust, you need to have prepared this magma in the lower crust. And Massimo Chiaradia studied this in quite much detail in this publication from 2-3 years ago, where he modeled the injection of basaltic magma in the lower crust and how it interacts with the lower crust through partial melting, hybridization, differentiation, etc. And what he highlighted that I think is very, very important is first to form a large volume of magma that contains a large amount of copper. This would be this pink dots here. You need a lot of time of magma injection in the lower crust, okay, several millions of years. Interestingly, in this region also, this is the region where you have high strontium yttrium values that are very typical to the values that we observe associated with porphyry copper deposits. And so there already you see that to prepare the ground for a decent volume porphyry copper deposits, you need to have at least 2 to 3 million years of magmatism, at least in the lower crust, to prepare some volume to be transferred to the upper crust. Of course, not all of it can be transferred, but if all of it is indeed transferred to the upper crust, then bingo, you have good chances to have a giant porphyry copper deposit. If only a tiny part of it is transferred to the upper crust, then you could form a moderate sized porphyry copper deposits. And this, of course, has most likely to do with the tectonic setting and the structural evolution of the location. And this is another topic, yet it's a very important topic. Right, so a long time in the lower crust to prepare a large volume of magma is required. Then, when you have transferred this magma to the upper crust, some volume, what would be really interesting is to try to estimate what is the volume of this magma. And a few years ago, with Bertrand, we have proposed a possible way we could do that, where by comparing the duration of the seen mineralization magma emplacement and the duration of the magma outgassing, which we could assume to be more or less equivalent to the duration of the mineralization. And in this diagram showing the volumetric intrusion rate of magma in the upper crust, and this on this axis you have the volume of magma that is used to form this deposit, we could actually plot few important deposits like El Teniente which highlight that just based on geochronology, you would need a few thousand cubic kilometers of magma to form El Teniente, which matches perfectly with the mass balance constraints. For Kelong in Tibet, you would need few hundred cubic kilometers, while from Bajo de la Lumbrera, you would need a few tens of cubic kilometers, which according to mass balance constraint is actually excellent. So this seems to be a plausible way to determine the size of the plausible size of the porphyry deposits. Of course, this is very coarse and very preliminary, and neglects many complications that exist in actual system. And this can only be done after an extensive amount of work and an extensive amount of dating, of course. This is not something that you do in the time frame of an exploration campaign. But something that is striking is that in many systems, actually, the volume of magma can be extremely big. This is an example from the Yerington batholith, where the total volume of magma is about 1,000 cubic kilometers. Yet only a very small portion of this batholith, here the Lure Hill granite, is actually the one contributing to the formation of porphyry copper deposits. So it seems that the volume of magma alone cannot make it. There are other factors. There are clearly other factors. And because the Lure Hill granite is, I think, is estimated to be 65 cubic kilometers about, and has been, and mass balance constraints suggest that it is enough indeed to source the 3, 4, or 5 porphyry copper deposits that exist, that have been identified at least in the Yerington batholith. Yeah, maybe an additional information of this diagram that I can mention in passing is this gray fill here that shows what you can do with varying the chemical variable. Essentially, you can change the possible size of a deposit up to an order of magnitude, maybe, by modulating the copper and chlorine content, and of course sulfur and other values within permissible or geologically permissible values. But you see that, and rightfully, Yerington plots in the middle of this field, which is to be expected. Okay. So if only a small portion of the magmatic system is useful, what to do with the rest of the magmatic system that is not useful to form porphyry copper deposits? And this is where I think we probably need to move to understand the thermomechanical constraints on how magmatic systems grow in the crust, or how they erupt in the crust. Because maybe something I didn't mention in this map here is that there is copious amount of volcanic rocks that have been identified in the Yerington batholith, and that have been thought to be sourced from the emplacement of these granite roots. So this could be one of the reasons why they are not used to produce porphyry copper deposits. Well, okay. So this is a regime diagram that looks complicated, but it's actually very simplified. And what you need to read it is for thermomechanics is to consider only 3 timescales: the timescales of magma injection in the upper crust, the timescale of viscous relaxation of the crust, because when you have magma injection, you need to make room for this new magma, and the way to make room is usually that the crust viscously relax, or and this would be the way to grow a magmatic system. Or if it's only an elastic process, then more likely you are not growing, but you are pressurizing the system and leading to an eruption. And the final time scale is the magma cooling, which in this case triggers second boiling and triggers the exsolution of fluids, because here we are dealing with hydrous systems, in these examples containing about 5 or 8% of water. And so in this diagram, if your crust is viscous, you would tend to have no eruption because you can accommodate the new magma that comes in the crust. If your crust now is elastic, then you have 2 regimes. either you have rapid crystallization, rapid injection and slow crystallization. So you would have eruptions that could be triggered by mass injection because the crust is elastic to a point, but at some point it cannot accommodate new magma anymore. So it builds over pressure, and then this excess magma needs to be vented through a volcanic eruption. Or if you have slower injection but rapid crystallization, and let's imagine if the crust is incredibly cold and your new batch of magma crystallizes very quickly, then this could also overpressurize your system, and this would be eruptions that would mostly triggered by second boiling. Okay. So now let's try to look at what we can do with this diagram, and this is the work of Medrit Townsend, Chris Huber, and I can't remember his name, Wim de Gruyter. And they ran some simulation in this parameter space to understand how magmatic system would behave. And in this top diagram here, the blue line show the extrusive-intrusive ratio. So essentially here, it means that you have 10 times more magmas that are vented through volcanic eruptions than magma that stay in the crust and form a pluton, while here, all of your magma, when it's zero essentially, means that all of your magma remains in the crust and forms a battleite. Okay, so clearly you want to avoid being in this part of the system, and you don't like too much being in this part of the system because you still have a 50-50 of the magma that is vented through an eruption and of magma that is that remains in the crust and forms a pluton. The red curve shows the volumetric growth of the system, and again, you would like to be in this corner of the diagram in order to allow growth of the system and in order to accumulate large volume of magmas to potentially form a large porphyry copper deposit. Here is the same diagram showing the magma chamber grows by mass, and here again it highlights that you should stay in this part of the system. Of course, this is not a static diagram, and in natural systems, at a given place, you would tend to move in this parameter space. At the beginning, you would have a fairly cold crust, which would be elastic, which would tend to trigger the cooling of new magma batch very quickly. So you would tend to be in this region of the diagram, and you may have some recurrent volcanic eruptions. However, with time, the more you inject new magma in the crust, you increase the size of your plutons and you battle it, but also you soften the crust, and at some point the crust may become more viscous than elastic, at which point you can actually grow a system without erupting. And this is possibly where there is the potential to form these porphyry copper deposits, because you essentially avoid volcanic eruptions in this part of the system. So my hypothesis or suggestions would be that you would need to preheat the crust in order to have a viscous crust. You don't want to have a very high magma flux. Otherwise, if you have a very high magma flux, you go back in this part of the diagram, but just a moderately high magma flux to the in the upper crust. And that you also want to have a moderately slow crystallization. Otherwise, you will be in this part of the diagram. And much of this you can do by preheating the crust thanks to precursor magmatism that we always see. And this is why I told you in the beginning, I think the precursor magmatism is really instrumental to the formation of porphyry copper deposit, because it possibly allows the formation of really large system by allowing magma injection in the crust without any significant volcanic eruption. Then the last part that is required is, so okay, now we have assembled a large magma body in the upper crust. It's partially molten and it's degassing, but we want this magma body to degas in a focused way that all the gases come in one place. And this is, I think, the results of very interesting simulations by the group of Stefan-Rich, where they have emplaced a magma body of this shape in the upper crust. And they have let it degas essentially using regime diagram for regime constraints for degassing. Essentially, in the center of the system, even if you form bubbles, the mechanics is leads means that actually these bubbles are very unlikely to be extracted very efficiently from this part of the magmatic system. However, at some point, around 50% of crystallinity, which corresponds to 850 degrees more or less for this type of magma, all of these bubbles can coalesce and form percolation channels or fluid channels, and they can interconnect and eventually get focused or channeled toward the same portion of the system. And very interestingly, here is the normalized fluid flux across the roof of this magmatic system. So if you just imagine a line here through the roof of the system, at each pixel you collect some amount of fluid that is extracted from this system. And here you see that during the first 20,000 years of the life of the system, of the cooling of this system, the fluids are actually degassed, outgassed in all directions. So this sort of ring or outgassing front is not formed yet because the system seems to take some time to become self-organized. However, already from 10,000 years onward, you see that the system becomes self-organized and that all the fluids are focused toward a very small apical part of the system. And this is exactly the perfect spot to form a porphyry copper deposit, because in the first few thousand years, if all the fluids are transferred in all directions, of course you just putting your copper in everywhere at low grade, and you will probably even not make any veining or any significant copper anomaly. But there, when all of your copper and sulfur is focused toward a very small part of the system, this is exactly where you can form your porphyry copper deposits. But this requires two conditions. The first one is a water-saturated magma upon emplacement, which is usually the case, but it's not. Well, it's the case for porphyry copper deposits, but it's not the case for any magma that is or any pluton that is formed in the Andes, for example, or in arcs. Because there are some plutons containing pyroxenes that you can see also in Yerington, for example, also in the Chuquicamata district. And you need a large enough volume of magma to survive several tens of thousand years before they have the possibility to become self-organized. And this is not trivial at all. And possibly this requires preheating of the crust, the preparation of the crust, but importantly, it requires a large volume of magma. This is not something you do with 10 cubic kilometers of magma. Okay. So in summary, what do we need? So to have a large volume of magma transferred to the upper crust, we first need to prepare this magma in the lower crust. So we need to have a long-lived system of several million years, and this is usually associated with the development of a high strontium over yttrium anomaly. We want also that because the magma in the upper crust can only be emplaced at a given rate, and this rate is not unlimited, usually it's around 10 to the minus 3 cubic kilometer per year, it means that the magma emplacement and magma outgassing needs to take several hundreds of thousand years in order to most likely form a supergiant deposit. How do we avoid volcanic eruptions? The best way to do that is to preheat the crust, for example, by precursor magmatism, which is everywhere in porphyry copper systems. And this allows this favor growth of the system. And this is actually a very similar setting to many of the super eruptive systems that do not erupt by overpressure, but rather erupt by the roof collapse. And of course, this is exactly what we would like to avoid as well. But it's also an indication that, as Jeremy Richards suggested, or Massimo suggested more recently as well, porphyry copper deposits are probably failed super eruptions. But they are not. They are certainly not normal volcanic eruptions, because it is not in the same regime of this regime diagram I showed before. And the last thing that is important is to focus the magmatic fluids to a narrow apical part of the magmatic system. And for this, we need a water-saturated magma, which you can evaluate by using fresh amphiboles, if you can identify them, for example, or to have some information about the emplacement depth of this system. And again, you need a large volume of magma. And I want to close with plausible ways to look at this and to identify, for example, a magma that would be similar to a magma triggering super eruptions. Chemically, they all look the same. A magma that triggers a super eruption, or a magma that stays in the crust. But from a zircon perspective, you can actually observe small differences. And the way we do that, at least here in Zurich, is using high precision zircon petrochronology, because it gives you the duration, the volume, and the growth, and potentially the growth rate of the system as well. And this is a very simplified way to explain how it works. Essentially, if you place a small volume of magma in the upper crust, it would cool, and zircon only crystallize within a given temperature interval. And this temperature interval you can gather from zircon using trace elements contained in zircon, for example, like titanium. And in the zircon record of this pluton, you would only have a very short duration that can be recorded. So all the zircons would have more or less the same age within uncertainty. However, if you take a bigger magma batch, you would have a much longer period of zircon crystallization. But in reality, the magmatic systems, most magmatic systems are not one batch. They're actually the accumulation of several magma batches assembled in the crust. And the kind of signal we could potentially see would be this one, when we have oscillating temperatures spread over a long amount of time. And this is exactly what we see in many plutons and in many porphyry copper deposits. But of course, depending on the growth rate, depending on the total volume, the inner detail of this pattern can change. And this is what we are doing and what we're interested in here. And the way we do that is by looking at zircon in quite many details. For example, first, analyzing the grains for trace elements, core and rim, and then dating this grain at high precision using chemical abrasion ID teams method, with which we can get really high precision, which is actually the precision needed to work with this, to use this approach. You cannot do that with laser, you cannot do that with SIMS. It's a matter of precision, but it's also a matter of accuracy. And ID teams allows for both, fortunately. And here is some preliminary results that we're publishing with Lorenzo Tavazzani, who they are not from porphyry copper system, but they are from large silicic eruptions versus silicic intrusive suites. And you can see that following essentially a statistical treatment of this zircon spectra, of this measured zircon spectra, you can really see distinct differences in between the systems that trigger large silicic eruptions, and this, so potentially the systems very similar to porphyry copper deposits, and the system that form essentially plutons that stay in the crust and accumulate there and do nothing really interesting. And so this clearly highlight the potential of zircon petrochronology to study this system and potentially identify as early as possible during the exploration process a large porphyry system. But of course, this is work in progress, research in progress, and I hope in the next 5 or 10 years we will be able to put actual numbers on all of this. Thank you very much for your attention. And yeah, I guess since it's the end of the year, I wish you a Merry Christmas and a happy end of the year.
Thank you, Cyril. Very good. Very interesting. We can see the importance of really understanding the physical, also the physical aspects of the magma chamber. So I'll just maybe Jeffrey Hedenquist has a question for Cyril. Sorry, I will unmute you. Yeah. Okay, you can unmute yourself normally.
Okay, thank you, Michael, and thank you, Cyril. Very clear development and explanation of some of the work that I've been reading by yourself and colleagues, and it really helped me sort of understand these factors and put it together. I really appreciate that. I have a lot of detailed questions. I'm sure others do as well. Perhaps, though, before we get to that, and given that there are some geologists in the audience from industry, can we step back and think about very practical recommendations, suggestions for targeting districts, targeting regions to go and explore for larger deposits? Prior to the type of zircon work that you're showing, et cetera, would you suggest, from your work, it would suggest that areas of lesser volcanic activity versus evidence for plutonic activity? As you say, you don't want to erupt your potential causative magmas.
Sure. Well, again, this is all very much work in progress, and at this stage, I would say it's mostly a reasonable hypothesis. But I would like to be careful not to give the wrong impression that this is working, because this is still being tested. There are good reasons why it could be working, but I'm very sure that along the way we will discover many details that are important and that I have ignored so far. Yet, something that seems to be important is a prolonged history of magmatism. Then when you come to a place, with a new place where you have indeed volcanic rocks, plutons, etc., something that I think is key is to understand the relative timing, but also the absolute timing of all of these events, that you can do very well with good mapping, of course, for the relative timing, and with a decent amount of geochronology. And already at this stage with laser ICP-MS, for example, you can already get a decent idea of whether you are dealing with a district which has seen 10 million years of magmatism, more or less continuous, or if you had two phases of magmatism in this district, and maybe a isolated phase that is no longer than 1 million years. This would already be useful, and then of course you would tend to look toward a part of the system which has seen few million years of seemingly continuous magmatic activity. And ideally that all the volcanic rocks are rather on the younger side of this system. Another part, of course, is to simply look at the basic petrology of the rock. If you have some rocks, well, if the earlier rocks have pyroxenes in it, it's okay. Let's assume they contribute to warming up the crust. But if the later rocks still have pyroxenes in it, just go away, of course. And I guess many exploration geologists already do that. However, if you see an evolution toward the systems being more and more hydrous, with amphibole, for example, then and also if you identify the highest transformer gem signature, this is where you can probably stay and investigate a bit more. Mm-hmm. But I guess this is already what exploration geologists are doing, part of that.
Oh, yeah, but always need to be testing our ideas. Another aspect that I really found intriguing, you're finding evidence that it is the longer lived systems or the systems in their later stages of evolution, that they're building larger magma chambers, and suggesting that some of the larger deposits may be later in the history of development of a district. And empirically, that's what Silito and others have noted, that the largest and highest grade deposits, porphyry deposits, tend to be the youngest in a district. We can go to a place like Escondida on a very large scale. The deeper, younger Papa Escondida and particularly Escondida Este are the largest, even larger than Escondida. So that may be evidence for your type of suggestion.
Exactly, and it is exactly the same in Chuquicamata, where early on you have this very small deposits or occurrence in the, I can't remember the name of this pluton, west of Chuquicamata. Then you have the Toki cluster, which is large, but an order of magnitude smaller than the Chuquicamata cluster still. And so here you have several million years of development of a thermal anomaly in the end that ends up being a giant copper anomaly. And yes, indeed, there are many evidence for that. And I would suspect that the process I propose here, this preheating of the crust, allowing for a very large magma chamber to grow in the upper crust, is possibly the one controlling this observation.
And also in the Mankayan district of the Philippines, where Michael has worked, you have three two barren and one small porphyry deposit that are the oldest. And then 800 meters deeper, the largest and highest grade, far southeast porphyry, is a very significant deposit.
Okay, okay. I'm less familiar with this system. I didn't know. That's interesting. Okay.
Yeah, well, talk to Michael and he can brief you on that. Yeah, I have lots of various questions. Michael, I haven't been looking. Do you have questions coming in from others here that you want to ask?
And then there's another question from Dina Klimentieva. If you want to unmute yourself.
Yeah, thanks. So thanks so much. Very interesting talk. And much of it was already answered and posed by Jeffrey Hednquist. So thanks for that. The one that remains, can you actually tell the focused fluid discharge from the dissipated fluid discharge if you look at the alteration halo in the field? Thanks.
I'm not fully sure. I would anticipate that this would be very subtle, actually, because there you would have, well, if you look at, let's say, a normal pluton that is hydrous, that has degassed, but is not associated with porphyry copper deposits, like, for example, in the Alps, where we see the Adamello batholith. And this one is full of amphibole, is hydrous, that's clear. It's a little bit deeper. But the rock we see today in the Alps is dry. It maybe contains 0.5% of water in amphibole and maybe possible micas. So for sure, this one has degassed. And yet, when you look in the thermal, in the aureola of the pluton, I'm not aware there is significant evidence for hydrothermal alteration. So it's very subtle, I would say. Where the hydrothermal alteration or the fluid rock ratios, let's say, starts becoming very high is when during several thousands of years, you have all of the fluids focused in a very narrow zone, and where you indeed develop all of this hydrothermal alteration we typically observe in porphyry systems. But when it's diffused, it's quite subtle because the fluid rock ratio is actually very low.
Thanks a lot.
Okay, I can go for the next one from Rajarshi. Yeah. So do you think that the same idea can go for the epithermal deposits? Because it's like a porphyry clan, so everything possibly gonna be connected to each other. So do you think that this large volume of magma gonna be responsible for formation of epithermal gold as well?
That's the tricky question. So there is of course another component that for epithermal deposits. Of course, you have the involvement of magmatic fluids, but you also have very strong involvement of the external fluids already because you're in the epithermal environment. And then, according to the work of many others, the work of Murakami, the work of Massimo Chiaradia more recently, and few others, it seems that the depth of the system and the precipitation efficiency are really the controlling factor. So from the work of Massimo, if I recall correctly, he has this paper last year, I think, in Nature Communications, highlighting that the precipitation efficiency is key for giant gold deposits. It seems that even over a fairly modest durations for epithermal deposits, you can still form supergiant deposits. And the issue with such supergiant magma chamber in the upper crust is that if they are too shallow, so if they are too, let's say, close to potentially forming an epithermal deposits, it means that the roof of the magma chamber is also very thin. It's only a few kilometers, maybe less. And there you have you're also much more likely to trigger super eruptions. So I would think that it's a neat balance between having a shallow pluton, not to allow the formation of epithermal deposits, but not a pluton that is too deep, but not, no, sorry, a shallow, but not too shallow, otherwise you would start a volcanic eruption.
Okay, thank you. The next question is from Jerry. Would you like to unmute yourself? Okay, it looks like I can go to it. Is the database of porphyry deposits and therefore the key factors of the formation of porphyry deposits biased by the tendency that ignoring the porphyry systems and porphyry style alteration systems, both large and small, with negligible copper tenderness?
Wait. Okay, so this is a very fair possibility, actually. And of course, there is a very strong exploration bias in this compilation I showed before. Yet, so it is biased maybe toward the largest porphyry deposits. That's clear, because of course, when people identify something small, maybe they pass away, or maybe actually in this compilation there are small deposits that actually are much larger than what they are in reality. So it is biased in this direction, but it can also be biased in the other direction, that maybe it's a small deposit because it's only a very small part of a much bigger system that is now eroded away. So I would tend to think that even if it's not maybe 5 orders of magnitude in copper endowment overall, it is at least 4 orders of magnitude. So even if for sure there is a bias, I think it would be very unlikely that it is a very significant bias that actually because still, even in the economic porphyry copper deposits, today it ranges for 1 million tons, and we know that the deposit is not bigger than that, and several hundreds of millions of tons. So at least of economic ones, we have 3 orders of magnitude. And if we include the sub-economic ones, which also are many, we could add 2 or 3 orders of magnitude, almost for sure.
Okay, perfect. Jeff, would you like to continue?
I have lots of questions, others, but again, coming back to the eruption versus non-eruption, many years ago, I remember talking with mappers in the El Salvador district, including Cochapodosis, really good mappers in the field. They mapped the district, and they claimed that there was no syn porphyry volcanic eruptions. And I thought, oh, that's strange. We have to have something getting to the surface erupting. But it now maybe makes sense that, as you say, you want to just tune it right so that these intrusions are getting relatively shallow, exsolving, giving their metals and the ligands and whatnot degassing, and yet not erupt anything significant to the surface.
Yeah, exactly. And there are many systems in the world where we clearly have magmas that is in the crust with record of ancient volcanic eruptions, but nothing is really happening at the moment. And so these places do exist, and this would be the good ones for to find porphyry copper. Well, the current places forming porphyry copper deposits. Of course, it's probably too deep to envision any exploration or extraction. This would be the modern equivalent.
Yeah, Sergey raised a point in the chat that in addition to forming the giants, then we also have to consider their preservation, the overall tectonic environment, and whether or not they are less or more susceptible to erosion, for example. So that's another factor to consider.
That's a very good point. I wouldn't really not know. I'm not sure there is any specific study or information that would go in one direction or the other. Conservatively, I would think that they have similar preservation potential. At least, well, if you can look at some districts, for example, in Chile, where you have supergiant and few kilometers nearby, much more modest deposits. And it seems that they went through the same history, the more or less the same erosion history. So probably there is not such a big difference in terms of preservation potential, probably.
Thank you. So we have another question from Dene Tarkif. Do you want to unmute yourself?
Sure. Thanks, Cyril. From industry, I'm used to the concept of a gap in volcanic eruption being significant for allowing, fluids and concentrations to build up. But I'm used to sort of the paradigm that this is caused by being in an overall compressional tectonic environment, and that we need a tectonic trigger to reduce the compression momentarily to produce a deposit. So just going back to your diagram of the sort of viscous elastic crust, what would be the relative importance on, the compressional versus extensional environment and the preheating?
No, so this is a very good question and a very important point. So this diagram and this study was done at static condition with no tectonic stress. Yet it is true, you're absolutely right, that the tectonic stress would be superimposed on this aspect, but it would only be superimposed, and the mechanics of the crust would still, in a way, remain the same, even in a compressive setting. If the crust, if you have a high flux of magma in the upper crust, the crust cannot be soft enough to accommodate the space for this magma. So it will erupt even in a compressive stress regime. So now we really need to understand where we need to put the boundary and what would be the exact role of this external stress on the transcrustal column, because there is also a very high chance, and this has been suggested many times and observed, that during a compressive stress, actually you can also reduce the magma supplies to the upper crust. So there are all of these things that balance each other and of course count. But I would say that it might not be the only important thing. It's on top of that, and yeah, essentially.
Okay, thank you. I got another question from Abdullah. Would you like to unmute yourself and ask your question? Okay, it looks not, so I'm gonna go back. Does the host rocks apply on the size of the porphyry deposits? And if the case for the old system, for example, Archean, Precambrian deposits, so how would end up getting a giant deposit when we end up the erosion as well? So it's erosion related, preservation related question.
Yeah.
Specifically in old systems.
Okay, well, thank you for this question. It's so the material that sources the copper and the sulfur is not the host rock, and so it is the underlying magma that degasses. This is the source of copper and sulfur. So from this perspective, you would be you cannot change the source by changing the host rock. Yet the host rock, of course, could have a very important role in trapping this copper, because in order to precipitate the copper, of course, you need cooling, but you also need fluid rock interaction and especially acid buffering. And this acid buffering can be extremely efficient in mafic rocks, like it is the case at El Teniente, and this is why I guess El Teniente is such high grade. It's around 1% on average. And you could also have a very good trapping conditions for this copper in carbonate rocks, where you usually have a high grade of copper, higher on average than in porphyry copper deposits formed in silicic rock. So it would certainly strongly affect the grade, but I'm not sure it would significantly affect the overall size. Of course, if it would make a huge difference between 1 million tons of copper with a grade of 0.1 weight%, which is not economic, and a grade of 2%, which is possibly economic in many places in the world. So in that sense, yeah. But the overall contained copper, probably not, or minimally.
Okay, so it affects the grade, not the size of the deposit.
Mostly.
Okay, thank you.
Okay, we have another question from F. Pagianini. If you would like to unmute yourself.
Hi, Cyril. Thanks for the presentation. So we know the relationship between strontium and heat film related with heat rotation and pressure of the magma's generation. But I have not so clear what's the relation between why high strontium electron ratios means a large volume prepared in the lower crust. Could you briefly explain this?
Sure. Maybe I come back to the figure of Massimo. So when magma comes in the lower crust and is produced in, let's say, in the mantle, it ponds in the deep crust, and there it starts differentiating. And of course, already, if you just differentiate in the lower crust, this magma would tend to have a high strontium over yttrium value. But there are some magmas that would differentiate maybe in the middle crust, etc., and would have different strontium over yttrium values. But and there are actually many strontium over yttrium magmas that seems not to be associated with large magma volume. But on average, high values of strontium yttrium would tend to be associated with large volume of magma. And this is how to say? In the end, the magma that is produced in the lower crust is not only a differentiate, it is also a mixture of differentiated magma with high strontium over yttrium, but also new magma batch that comes from the mantle and eventually form an intermediate plutonium composition. In addition of that, you have the crystal melt, which is maybe 10 to 20% of the overall mass of the pluton that makes it into the magma. So it's quite difficult maybe to have some intuition of how all of these factors plays together. And I guess this is the beauty of Massimo's work, that accounting for all of these variables, it clearly identifies that you need actually, although you can produce locally high strontium over yttrium magmas, you're much more likely to produce this magma after many millions of years of magmatism in the lower crust. Let's say it's a probability thing. And you're probably aware that even with high strontium over yttrium, there are a large amount of false positive. And there are also a large amount of false negatives. There are many porphyry copper deposits that have moderate strontium over yttrium values, actually.
Okay, thank you.
So yeah, I would refer you to a detailed read of this paper by Kiradi and Kariki. It's open access. It's in scientific reports.
Sure.
Aaron, would you like to jump in and ask your question?
Thanks. No, thanks to Cyril and the ODH team for this. I just had a quick comment or question on the erosion question that you looked at earlier, and that's just, is there any difference in the general emplacement for the big porphyry systems compared to smaller volume porphyries?
In the depth?
Yeah.
I have no idea. I would not be able to say, to be honest.
I guess this is something Massimo was looking at in terms of metal content and depth of porphyry emplacement, but I didn't know if there was a size relationship with this either. I
don't know. Maybe Jeff, do you know about that?
I'm just thinking, and of course, the deepest porphyry that's been suggested to have formed of any size that have been well studied is Butte. It was suggested about 6 kilometers deep based on fluid inclusion studies, critical behavior fluid inclusions. And that's about 15, 17 million tons of copper, very high grades. But yeah, I'm not really, I don't know anybody who's really tried to quantify sufficient number of deposits. Interesting thought.
It just goes into the preservation issue that was asked earlier that made me think about that. But
no, of course. And on the other side of the spectrum, Chuquicamata is a copper moly deposit, and moly is suspected to indicate slightly deeper conditions, maybe not as deep as butte. I don't know, but I don't know how Escondida is in terms of moly or El Teniente. I would not be able to say.
And gold-rich porphyries, Silto argues that gold-rich porphyries porphyry coppers tend to be relatively shallower than copper only.
Yeah, exactly.
But you still have some very large Ollantaytambo, very large porphyry copper deposits with high gold.
True. Then I guess what really matters, what could potentially matter, is maybe not where the deposit is formed, because this has much to do with hydrology and potentially aided by faults. But I would suspect that the depth of the underlying magma system or the underlying magma chamber potentially is important, and maybe there is a tendency for supergiant deposits to have magma chambers that are slightly deeper than other ones. Maybe I'm not really sure about that, but possible.
Would that relate to crustal thickness, ranges of crustal thicknesses? And if we're looking at things in the lower crust, a thicker crust would make it a lower or a deeper magma chamber. Or is that does that not?
Yeah, possibly. I guess indeed you would have some constraints from the tectonic stress in general, which would be associated with a thicker crust. In general, large porphyry copper deposits tend to be associated with overall thick crust. But I'm not sure there is a strong difference between a crust which is 40 kilometers thick and a crust that is 70 kilometers thick.
Okay, I think we got one more question from, and then would you like to ask your question?
You know, quick and dirty, I think of hydrous magmas at high pressure suppressing feldspar or plagioclase crystallization. So strontium doesn't go into the calcium site, so it builds up in the magma.
Exactly, yeah. No, this is probably something that I forgot to mention. Yeah, this is really what happens in the lower crust. But then, and if effectively, you see here in this diagram, already in the first few million years, the first injection would differentiate and form magmas with very high strontium overture value, like extremely high. But the ones that form porphyry copper deposits tend to have mild values between 150 and 50 maybe. And for these ones to form, you need several millions of years, because the magma that result from this differentiation is actually one that is a mix between this residual magma and new magma batches that have much more moderate strontium overture values.
Okay, so possibly that would be related to my question as well. So I do work in Ecuador, and zircon petrochrome is going to be a little bit expensive for me. So I'm just wondering, like, is there anything cheaper, something creative that we can use? Because the rocks that you see are pretty similar. Like, even I do get some porphyries that they do have biotite in them, but it has nothing to do with mineralization, or possibly it's not discovered yet through illegal mining. So I'm just wondering, something that I can convince the industry that, okay, this is much cheaper and I can get to the result much faster.
Well, I guess this would be certainly ideal, but maybe it's not too realistic yet. What is realistic and relatively cheap and incredibly needed, and I answered this a little bit before to Jeff, is very good field mapping. And it's a reality that good field mapping had been done decades ago, and we tend to do less and less. And this is quite unfortunate, because with good field mapping, you could already see a lot and already have a lot of information on the relative timing of the magmatic events and sedimentary events and whatever at a given place. And this is already very rich in information.
Okay, but I don't think that this would work for Ecuador. It's a deep jungle here.
Well,
we're facing like various issues and somehow.
No, sure. Well, a few years ago, I discussed with these people of the project Cascabel in Ecuador, and they seem to have really done a big job in mapping and doing good mapping of the system. And obviously, they were successful afterward. And I think this is really one good way forward in general.
Yes, pretty much I could get a lot of community guys to send to the jungle, not our students, just so you know. So that's a little bit problematic working with the industry.
No, of course. No, that's I understand it's difficult in many places.
Yes.
Okay.
So it looks like we really don't get that much questions. Possibly, Jeff, if you want to add something.
Well, just to follow up with this previous train of thinking, Cascabel was found by geologists getting into the deepest, most difficult ravines and looking at outcropping, the outcropping geology, interpreting the alteration and finding some sulfides or supergene relics after the sulfides. And Cyril's point about getting into the field, starting off with some good mapping, is essential, and then taking the research insight from someone like Cyril and other colleagues and recognizing what are some of the fundamental characteristics that are critical. And hopefully, Cyril, as you develop more understanding, you will be able to come up with proxies, guidelines for the people in the field.
Exactly, and new tools. Of course, the existing tools for in exploration, they are working, and they are working very well. But what I aim to do is to produce an additional tool that could maybe help. For example, when they discovered this outcrop, I guess they had the question, oh, it's interesting. Is it a big one or a small one? Well, it turns out it's a very big one, but in many other situations, maybe it would have been a small one. And then with potentially what we are developing, there would be a way early on to say, okay, you're most likely dealing with a big one, most likely dealing with a small one.
Yeah, I have invited Dr. Steve Garvin for next year. So just wait a little bit. So we're going to have a kind of story on this subject. And never forget, for the Cascabel district, it's right. Alpala deposit is right on Toachi fault. And that fault is like a giant thing, continuous all the way to Mekuchi formation. So whatever we are getting out of porphyries, VMS deposits, pretty much related to that shear zone in that specific area. Yeah. So in somehow structure is another point.
Yeah. Well, there was a talk a few months ago by Jose Piquer from Chile discussing the role of this transcriptal fault, which was very insightful and very interesting.
Yes. It's a multi-factor subject. Okay, so it looks like we really don't have any more questions. Lots of thanks for this talk. It was such a great learning process, and somehow I can use all of these things in my teaching. So, Aaron, would you like to add something at the end?
No, I just want to say thanks to Cyril and Jeff for coming along with a lot of basically getting this discussion rolling. It's been a really good discussion, and for me, this is one of the best. It's one of my favorite parts. So I'm happy to hear about it and happy to be a part of this. Thank you to Azam and Michael for hosting this.
Thank you.
I guess I get there's news. The link is not working for the certificate, so I will fix that. And if you need a certificate, you can email us at info@OreDepositsHub, and I can help get the certificate of attendance up.
Perfect. So let's finish off for 2021. I'm wishing you guys a very, very good 2022. Hopefully this pandemic gonna be under the control and we can do a little bit more field trips and traveling next year. And happy holidays. Cheers. Thanks very much.